let's look at another example of a Fourier series. So we'll do another fairly basic function, just the identity function f of x equals x on minus L to L, and see what we can learn by studying this guy. So when we go to compute the Fourier coefficients, an is going to be 0 for every n, because when we take x multiplied by a cosine function, we're going to get an odd function. So an integral of an odd function on a symmetric interval is always going to give us 0. If we look at bn's, we get a little bit more juice. So we have the integral from minus L to L of x sine n pi x over L dx. And so then this involves doing some actual work. I recommend using Mathematica or some other computer algebra package. And the answer is, I mean, you can do it by integration by parts, but probably at this point you don't need the practice doing integration by parts because you can do it well enough, right? Okay, so then cosine n pi minus, and then we have sine n pi over n pi. And I just wanted to point out that if you do use a computer to crunch inner products, the computer doesn't necessarily know that by n you mean an integer. So you have to look at this and notice, oh, that term is actually 0 because sine is 0 at every integer multiple of pi. So that simplification is up to you. And so this becomes 2L over n pi times minus 1 to the n plus 1. Okay. So then we have that our function has a Fourier series of 2L over pi times the sum n equals 1 to infinity minus 1 to the n plus 1 over n times sine n pi x over L. And if we write out some terms of this, what it looks like, 2L over pi, and then we've got sine pi x over L minus 1 half sine 2 pi x over L plus 1/3 sine 3 pi x over L, and so on, right? Okay, so now we're going to make some observations, studying this guy a little more closely. So first observation, if we take the derivative of both sides of this and differentiate term by term, on the left we have that f prime is equal to 1, and on the right we have 2 times the sum from 1 to infinity minus 1 to the oh, hold on. Sorry. We're not over n anymore. We just have that guy on the ground. All right. Cosine n pi x over L. And that series on the right-hand side doesn't converge to anything, much less 1. So differentiating term by term fails. So what else can we observe by looking at this one? Well, we saw from our theorem that the Fourier series of f is always going to converge to f in the L2 sense, in mean square. What about in the that was by a theorem. What about in the other senses? Well, so let's look at well, if we evaluate this function, the Fourier series, if we evaluate the Fourier series at the endpoints of the interval plus or minus L, then what happens is you have every term, just going back to this right here, you can see these are going to cancel, so you have sine of pi, sine of 2 pi, sine of 3 pi, and all those things are 0. So every summand is 0. So the entire thing disappears. And in particular, you don't get minus L or L as you think you should. So what we learned from that is that the Fourier series for f does not converge to f pointwise, at least not at the endpoints of the interval. Now, it actually turns out that it converges pointwise everywhere else. So if I evaluated at x, that converges to f of x for x in the interior of the interval that we're looking at. And then we can also ask the question of what about does the Fourier series of f converge to f uniformly? And so what do we have with that one? That, let me see, get a picture going on here. There we go. So here's a picture of the first 5 or 10 Fourier approximates for the for this series here, and you can see things are not going well. So in particular, there's this distance right here, and everything is staying bounded away from x by at least that distance. It looks like one of those Gibbs phenomenon type things, right? So it turns out that this does not converge uniformly as well. So what's really going on here? Let's take a look under the hood. So we say that a function on the real line is periodic if there exists some number p, some positive number p, such that f of x plus p is equal to f of x for any x. And so that just tells you that if you shift the graph of f by p, then it matches up with itself again, right? And so then the period of f is the smallest such number p, right? So we say that sine and cosine are 2 pi periodic functions. We don't say that they're 4 pi or 6 pi periodic functions, even though if you shifted them by that amount, their graphs would match, right? And so because we want to talk about the smallest such p, we also usually require that f to be a non-constant function in order for it to be called periodic. Otherwise, you end up with something that has period 0, which is a little bit weird. So what else do we have? Okay, so that's if f is a periodic function on the real line. Well, if you have something that's not periodic, you can make it periodic, sort of. So now this is for a function that's not defined on the entire real line, but just on this symmetric interval. So the periodic extension of f on minus L to L, so we extend it from f to r by periodicity, so requiring it to be periodic. So I'll give it a little wave there to make it look periodic. And so the way this is defined is that for values of x that are in the original interval, the extension is just equal to itself. And then for other values, what you do is you evaluate f at x minus some integer multiple of p, where x minus np now is in this interval so that it's well defined. And it can be shown that there's a unique integer that will make that true. So if we now look at the 2L periodic extension, so by that I mean the periodic extension with period 2L. So the 2L periodic extension of our example function x is going to look like, let's draw some picture here. So we've got something that's going to be oh, actually, sorry, so we started with, there we go. So that's what we look like on the, heck. There we go. So that's what it looks like on minus L to L. And then I'm going to extend it from L to 3L like this. And I will extend it to minus 3L to minus L like that. So that's the periodic 2L periodic extension of f. And this tells us what's really going on with the failure of uniform convergence. So if we look at the graph of what's going on a bigger region here, we can see that because the sine function is periodic and it's defined throughout all of R, it's actually experiencing this sort of break or jump here, and so now you can see that really is a Gibbs phenomenon that's happening at the upper and lower end of the interval. And so here's L and minus L. I'm using L equal to pi. Maybe I should just write pi. And so that's what's causing the problem and the failure of uniform convergence.